which is Simon Gabriel Beauvais. He was supervised by René Doyon, and he's going to talk about the impact of telluric absorption lines on high precision radial velocity measurements.
Yes, hello. I would show myself, but my camera doesn't seem to work today. It's a bit capricious. So yeah, I'm going to talk to you today about the impact of telluric absorption lines on high precision radial velocity measurements, especially in the context of Spirou, and in fact it's going to take measurements rather soon. But here's the general context, as to say. We want to detect a planet like Earth, Earth in the habitable zone of its star, as much as possible. The Earth induces a movement of about 9 centimeters per second on the Sun in a radial velocity sense. A planet like Earth, were it around an M dwarf and we were to observe it, would induce about 1 meter per second velocity. It's about the speed at which we walk on its own star. And there's a lot of M dwarfs that are in the close vicinity of the Sun. But the M dwarfs are mostly infrared stars, being that they're very small and quite cold. So just for those that don't know what radial velocimetry is the measurement of the reflex movement of us induced by its planet on its O star. And being that the planet from our point, the star from our point of view moves around the on the line of observation, it through Doppler and induces like a shift of its lines around. Well, around the null velocity, or around the velocity we'd expect to find the well, those lines. So that's what we're trying to measure by with that technique. And as for Spirou, it's a spectropolarimeter in the infrared. Here's some of its quick specs. Those we care most about is that it's designed for precision of 1 meter per second. So it's designed to be able to measure those Earth-like planets around them dwarfs. It operates in the infrared, which is good for to measure on those types of stars. And its spectra tend to be split into 49 orders, which is a bit of a conundrum that we have to solve if we want to do a measurement, a full, complete measurement of the spectra of a star, which we end up with 49 spectras. And here's what the preliminary results look like that I took from Etienne Artigot. It's supposed to be a white lamp. We notice that there's some bands separated, some darker parts. Those parts are due to the atmosphere, which is the reason why we want to qualify the impact when it comes to radial velocity measurements, because they do tend to take quite a lot of space on the spectra. And that problem translates to, on the atmosphere, coming from the atmosphere, that this is just a 6 elements, the spectra of 6 elements on the atmosphere. We find that there's the regions where we don't find any transmission, there tend to be those in those vicinities. And it's, well, trying to find anything through this is terrible, very difficult. So to quantify the impact, we went through data simulation route. And we started with the Phoenix Stellar Atmosphere Library, which is, well, it contains a lot of different stellar types, and it was very, very high resolution, so we could downgrade it easily to the instrumental resolution we needed. We moved it to the speed that was relative to the observer, so we induced the velocity shift that we wanted to measure on it. We applied the telluric spectro through it, so as we simulated the transmission through the atmosphere of that spectra, and we varied the weight, so to also reproduce the telluric removal process that is done by several different techniques and several different DRS that do their own things with this. But with a varying weight, we expect that would reproduce most of these methods. We degraded it to the Spirou resolution by convoluting it with the kernel that was proper for the instrument, well, as much as possible. And we made a mask, because whatever happens is always going to be a step that we can't take away with all the techniques. There's always parts of the spectra that we don't get any signal through, so we might as well mask them. And we corrected the rest of the tellurics. In our case, we went and used the Barnard star, the GL699, which is an M dwarf of 3,200 Kelvin. And we use the Tappa spectra coming from the Mauna Kea sky, where Spirou is right now. And we assume an angle of 45 degrees. so as to get as much tellurics, but not too much, that we wouldn't get anything at all through it. The algorithm we went with, because to ensure the a good quality measurement, is based upon an expansion in the velocity space of the spectra. I'm leaving the proof to the reader to redo that calculation, but it's an iterative process in the sense that it's a first order expansion that we do of those spectra. And it also tends to be much more precise than the cross correlation or majority of other techniques available right now, and extremely robust to the presence of tellurics, which is a good thing when you have so many to deal with. We also have we also added an analysis algorithm to quantify that impact. Now that, bear with me, this part can get rather complex. So through a night, we have the end section of the spectra, because we don't assume necessarily 49. It's more of a generalist approach. We have n section of a spectra, and we have m observation throughout the night. So we end up with, well, good quantity of different spectras. We take one of those orders throughout all the observations, we make a weight out of it. And so we do for all the different orders. So that gives us an idea of the quality of that region of the spectra throughout the night. We take all these weights, and then we do a weighted average coming from all for one observation, we do a weighted average. And then, oh, I'm sorry, not from one observation, from one order, we'd get a weighted average throughout the night. And so we get basically m measurements, and from that point we can do statistics or average it or do whatever flavor of distribution we like with it. But that gives us a good idea of the radial velocity of that exoplanet at that specific during that specific night. It does assume, though, that the planet doesn't move much throughout the night, so we have to assume some sort of stability, or that its period is much greater than about 8 hours, but it's generally speaking rather accurate on that sense. Their specificities, though, to allow for the discussion to go for the following discussion, is that the telluric weight is defined as the minus tau at e to the minus tau, where where a weight is added before, so as we just reduce it following the Baer-Lambert law. And in a sense, that means that if I put a weight of 0, we assume a perfect telluric correction. If I put a weight of 1, we assume there's no telluric correction being applied. So anywhere in between is well, semi-corrected. And there's also the mask threshold. It's just defined as the point where below which a line is identified as being too deep to be corrected for. We convolve the box that the mask gives us, the part of the spectrum, we convolve it with the instrumental resolution so as to widen and catch the entire ray. So that means that visually, if I put a threshold at 0.4, those lines would be removed, but not just the tip that gets below, just the entire line itself. So that allows us to identify the regions that we don't think we can correct. So the first results we found was that there seems to be a strong correlation between the error and the barycentric velocity of the Earth. But it also means that between the telluric spectra and the star, there's a possibility that lines correlate or fall one over the other, and there's no way to discern them. So by moving the spectra, we find that there's error structures that also tends to move, showing that there's an importance at choosing when you want to observe, if you want to maximize the precision you're going to get, especially when we reach levels of the meter per second precision. Now I've amplified the signals on those two figures to more readily show those structures. It's more of the order of 50 centimeters to 1 meter per second difference between the highest error throughout a year and the lowest error throughout a year. But in this case, we find a minus 10 shows the 3 peaks moving to the left, and the plus 10 shows 3 peaks moving to the right. So that's going to be something to take into account when we want to achieve the highest possible precision on those measurements. And the second result that we found was that depending on the wave of the tellurics we put in the mask, we find the maximum theoretical error that the Spirou measurements could reach. which in our case would be if you put a very low mask and you put about 10 to the minus 2 telluric weight, which would assume a very good correction. You could reach about 1.3 meter per second. A more realistic scenario was closer to about 10 to the minus 1 weight. And in that case, it's about 80%, which you'd reach the highest precision. So it gives us like a ceiling, like a floor to reach precision-wise. But now all this is all simulation work. If we compare it with actual Spiru data, we took the observation of GL699 from the August 4th in 2018. All the parameters of the star were added in the simulation. And we found 1.99 meter per second for that night from the Spiru DRS, and 1.5 meters should be the minimum they should be able to reach. So yeah, throughout that night, it would be doubtful you could go lower than that according to the algorithms and the simulation that was done. But so that gives us that tells us there's about 49 centimeters left in the various possible errors within the DRS. So the algorithms still need a bit of work on that. So the take-home points here is that the high precision radial velocimeter it's not going to be possible throughout an entire year if there's no characterization of the star and the telluric strata. We don't characterize correlation between both, as they could sum up and just skew the results to be very much worse than they should be. And if we don't do a proper handling of the tellurics, we could find we could reach terrible error levels, and without even knowing about it. And the Spiru DRS is getting very close to its theoretical limit. So there's still a bit of work left to do, but I mean, without better analysis techniques, it's going to be very hard to guarantee the meter per second throughout the year. So any questions?
I have a question. So if we pessimistically say that we will not develop any new techniques that are better than the current state of the art, then basically Spiru is limited to about 1.5 meters per second precision. And so am I right that just means instead of finding an Earth-sized planet in the habitable zone of an M dwarf, you find like a 1.5 Earth mass planet in the habitable zone of an M dwarf, which also sounds fine to me?
Well, I wouldn't know if it is exactly 1.5 mass, but yeah, it would mean that we'd find something. We'd have to find a planet that would give a higher radial velocity on its host star. The techniques, though, there's several other techniques right out there competing. Some show higher possible precision, but are much more sensitive to tellurics, while others show higher robustness to tellurics, but lower sensitivity. So it's a matter of figuring out which techniques to apply. Right now, this one is the one that is used within the Spiru DRS, and it somehow means that it's going to be important to choose when we observe as much as it is to choose what to observe.
What right now is in the DRS is the PCA method, no?
For the tellurics removal, this is just a part for the actual velocity measurement. So once we do the PCA, we should reach the level about 10 to the minus 1 on the weight of the tellurics. So about that region. So that's give or take the performance works they have right now. If we apply the algorithm for measurement afterward. So any other questions?
Okay, if there are no more questions, then our next speaker is Melissa. And Nick, how about you introduce Melissa?
Is Melissa online? I just got an email from her. She's in some other meeting and is going to try and Skype in. But if she's not online right now, I don't think there's any point in introducing her. So
that makes sense.
Yeah, I'm looking through the list of participants and I don't see her. So I think we should just punt on her. Oh no, there she is.
Yeah, she just joined. Okay.
We nipped it in the bud, which was good, but it might come up again. Because we have another abundance of.
So Melissa, are you? Can I confirm that Melissa is there? Hey Melissa, can you unmute yourself so that we can make sure that your audio works? So we still can't hear her. Well, anyhow, I'll go and optimistically introduce her. So Melissa Marquette is a master's student in the Earth and Planetary Sciences department here at McGill, working with me. So she was previously an undergraduate in the astronomy program at Berkeley in California. And then after she wrapped up her undergraduate degree at Berkeley, she worked on the MAVEN mission, which was looking at atmospheric loss on Mars, and did a couple of papers with the MAVEN mission before coming to McGill, where she's working on eclipse mapping, and in particular eclipse mapping at high spectral resolution, ideally with Spiru. So she has some approved Spiru time, and is currently working on more of a theory proof of principle paper describing that, which I presume is what she will talk about once we can actually hear her or see her. So Melissa, you're gonna have to share your screen if you want to do something.
Yeah, I just installed this software because my computer doesn't like it, so we'll see if this actually works. But how's that? Can people see that?
We can see a screen of death on someone's browser. Oh yeah, now
Perfect.
PowerPoint. Yep. Yeah, I see it.
Yeah. So when I go full screen, this crashes. So this is gonna be how it is.
Okay, I'm gonna mute myself and go ahead, Melissa.
Yeah, we'll see how if my internet holds out, but for now, thanks for the introduction, Nick. I'm Melissa. I work on characterizing hot Jupiter atmospheres through high resolution eclipse spectroscopy, and I'm just going to talk about that a little bit right now.
Yeah, how was the game, man?
So,
It was a lot of fun.
the first thing that most people think about if you're not an exoplanet person, if you say hot Jupiter, is transit spectroscopy. And so in transit spectroscopy, we observe the planet as it passes in front of its star, and the light from the star then gets filtered through the atmosphere of the planet, and we analyze it. And that's going to be delayed. All right. But the reason that I care about eclipses rather than transits is because we can observe the planet in its own light. We get a different perspective on the planet. For transit spectroscopy, we're looking at the terminator because we're looking at what's being filtered through the atmosphere and coming towards us from the star. Which makes it a little bit more difficult to detect. But there's a boost from looking at the day side. It's also hotter. So apparently my high CPU usage is affecting the quality. Sorry about this.
We scored like 3, maybe 4 goals, like super.
Hey, Melissa, given the technical difficulties, how about you delay this presentation until the next Teps round of presentations, if possible? Because it's really hard to hear you. I think there's a lot of background noise and weird interference stuff.
Yeah, I would agree with this. I think it's an interesting topic, and we want to have this in the right way. Maybe the best is simply we can look in the calendar and somehow add you on the next month presentation.